Hello guys, this is Sumedh here. We'll be covering aggregate planning and the chapter 13 from the 12th edition of Operations Management by Heiser and Munson. In this chapter, we will be looking at how to do the planning such that we can, let's say, match all the demand with the capacity planning and so on. Now, this is still at the aggregate level, yeah. So the major concept, I mean, there are particular strategies as to how you can influence the demand because we cannot predict the demand, but we can certainly influence it by, let's say, running advertisements and so on. And there are certain strategies as to how you can adjust your capacity to for either for production or the service by using part-time workers and so on or seasonal workers. Now, one of the mathematical approaches that I want to show you in as an example is the transportation method. Now, this is the time we do have the module of transportation models, wherein we will go in the detail, but this is more of an introduction. So let's say you have a scenario wherein there's a capacity when you have a choice if you were to produce in regular method, overtime or subcontracting, and there are different costs if you were to go either way. And you also have, let's say, inventory, and if you were to produce in one period and you move on to the next one, then you have certain holding cost. Also, there are different targets that you are given. Let's say the demand for the March, April, and May is given as 800,000 and 750. Of this 800, 700 can be produced in regular time. 50 maximum can be produced in let's say overtime, and no more than 150 units can be produced in subcontracting. If you were to produce regular time, it costs $40 per unit. Overtime costs $50 a unit, and subcontracting, like outsourcing it to somebody nearby, costs you $70. If you were to produce in one period and carry it over to meet the demand of the next period, then you end up spending $2 per unit of a storage cost. Yeah. So we're going to do the similar example that we have from the end of the chapter problems, and we have something like this. Now, let me reset this, and so then we have the firm. Let's see if you can see this now. Okay, we are given a scenario wherein the information given to us is that regular time we have 30 units demanded. I mean, the capacity is 30 units. Overtime, you can produce up to 10. Subcontracting, only 5 can be produced. The demand forecasted for this period is 40. Similarly, for the second period, you can produce 35 in the regular time, 12 in the overtime, and 5 in the subcontracting. And we have a forecasted demand for that period, about 40 units. Similarly for the third period. Now we also have the initial inventory of 20 units, and there are costs for regular overtime and subcontracting for 100, 150, and 200, and the holding cost or the carrying cost is $4 per unit. Now let's see, the easiest way to solve this is the transportation method, which is shown in our PowerPoint, let's say as an example here. Now, this is from the old days when they used to do this on pen and paper, but the basic concepts remain the same. We would be using Excel because it's only good for, let's say, solving few periods at a time if you were to do on pen and paper, before it becomes almost impossible for humans not to make an error. The basic concept that is introduced in this transportation problem, this is, let's say, a specialized case of linear programming. In the transportation problem, you have to make supply equals to demand, okay? And in order to make that supply equals to demand, we add this what's called as dummy variable. If it's not there, it's highly recommended that we always make it. So in this rightmost column is the total capacity available. This is the supply, okay? But this is the dummy variable, or the excess capacity, or however you authors may call it in the textbook. But this is done such that the total supply matches, total supply matches the total demand. So total supply would be from here. All of this should equals to the same number as the total of this row here. Okay, so by doing so, you can follow certain pattern that makes our life easier, such that um, let's see, Control Shift D, anything uh, in for any given period, this is the cost, and here we write down the number of units that we can allocate this. So the method of representing this table is that you write column, the cost in all of these colored cells here. So these are all the costs if you were to allocate any unit, and then you start to allocate, let's say, certain capacity, certain number of production capacity in any of these corresponding spaces in white, okay, such that you follow the lowest cost in a row, such that you never exceed what your capacity is. So they've allocated 100 here, 700 here, which matches this, and then 50 here, which is equals to the maximum capacity. Let's say if you were to end up not using all of the capacity. So let's say in this case here, even though the capacity is 150, they only allocated 50 here, because at some point the sum of all the columns should not be more than what is demanded. It's otherwise it'll be like force feeding somebody. So if you see 700, 800 plus this 950, 950, and this 1000. So there's no point in making 150 here, because otherwise we will be making 1100 here for the period 2, which is not required, only 1000 is demanded. Okay, so that is why they have not done this. Now, since we only allocated 50 instead of 150, now we have an excess, so that is given here. So in the dummy variable. Now the way at the end of the day, what matters is you allocated 100 units at the cost of 0, you allocated 700 at the cost of 40, or in this case you made 150 units at the cost of 72 per units. So in the same manner, you in the dummy column, you made 100 excess capacity at the cost of 0. Yeah, so 100 times 0. So this does not affect our solution. Okay, now what we do in spreadsheet is that we make all of these cost cells at one point, like as a one table, and all of these white spaces as a table 2. Okay, and I'll show that to you in a minute. So oops, Control Shift D, and this one. Okay, so let's put in all the cost functions first. So all of my costs, let me color them the same as this, this, and this. Oops, I forgot this one. Okay. This, and this. And the way we can design this cost function, cost table is, let's say for example, the given values to us were, I want to see this together with this. Okay. So at this point, $100 is given to me as the regular cost, yeah, which is here. So let's see. Okay, should still be visible. So keeping the same format, I'm designing only the cost tables, yeah. So for now, the given information to me is that it costs $100 to make in regular time. Now I've only given this as January, February, March instead of period 1, period 2, period 3. Yeah, it'll be the same. Just for the sake of explaining it to you guys. Okay, so 100, 150, and 200. This is coming all from the information that is given to us. So 100, 150, and 200 is given to us. Now, if something was to be produced in regular time in the period of January, but was used for the period of February, then we have to add 100 plus the carrying cost, or I've added this here. I'm going to freeze this cell. Okay, like that. Okay, and also if you were to produce something in regular time, that would be same as regular time of the January. So I'm going to copy this, Control C and Control V, same as equals to this one. So the regular time and overtime and subcontracting for the any period that is current will stay the same. Yeah, so this is same as this one and same as this one. Yeah, or one way to do this would be, let's say, let me make it a little more clear. Okay, and I'm going to color this slightly different, such that this is equals to this. Yeah, and so the last one left over would be this one, which is if you were to produce something in January. Yeah, so this is, let's say if you were to produce something at regular time in January, but you were to carry it over in February and still not use it, and then carry it over in March, then there would be two periods that you stored it for, and therefore you'll have to add 100 plus 4 plus 4. Yeah, because $4 is our carrying cost. So we're going to say equals to this plus additional 4 units, and I'm going to freeze this so that I can copy it down. Okay. Now also, because this is excess, or I should say dummy, okay, the cost of this we'll assign as 0. The reason is if we do not use the capacity, it does not cost us anything. Okay, that is the assumption of the transportation model. Okay, and the idea is that it's better to have excess capacity, either to drive down your competition if need be on any given day, or the strongest point is not to produce something that is not demanded. So if it is not demanded anywhere, why produce it? Therefore, its cost of production is 0. Okay. Now the initial inventory in this case is given to us as 20. Yeah. So equals to 20. Okay. Now, oh, I already had it. Okay. So at this point, let me show it to you from the beginning, so then it's more clear. So first thing I'm going to say is the cost. If now this part would be the white cell. Yeah, so this is the table when I'm going to assign the quantity. So this completes this orangish yellowish thing, refers to all the cost table. Now the corresponding here, all these cells, let me color them so then we can talk about them. Let's say the green ones. Okay, the green ones, all these green cells refer to these blank spaces where we are supposed to allocate in the transportation table. Okay, so first things first, anything that we allocate should equals to what is demanded. Okay, so what is demanded in this case? The demand given is 40 for the first period, equals to 50 for the second period, equals to 40 for the third period. Now this is what is given. Also the given supply is 30 for the regular time for the period 1, Yeah. Um, Overtime is 10 and is 5 for the subcontracting. So this is for the first period itself. Yeah, so I'm just copying the given information here. So this much of information is represented here: 30 in regular time, 10 in overtime, 5 in subcontracting. Okay. Similarly, all of this information from here onwards will come here: 35, 12, and 5. Okay. We've already put the demand at the end of the columns. Okay, let's see. So equals to 35 equals to 12, oops, equals to 5. Now for the third period, same process. We can make 30 in regular time, 10 in overtime, and 5 in subcontracting. Okay. Now if you remember from the linear program, this in essence is our RHS. Okay, this is the limit. Similarly, if you were to look at this 90-degree tilted, this becomes our RHS. Okay, in a way, let's say here I'm going to say this is our RHS here. This is the RHS for the demand, this is the RHS for the supply. Okay, now at this point, let's sum up SUM, oops, equals to sum of the total supply that is available. And if I was to also say sum of all the demand, okay, now you see the balance is not there yet. So the supply available is 142, but the demand is only 130. So there would be always a surplus of 12 units that will be left unused. Yeah, unused. Yes. So it is better, before we start solving, what the transportation method says is that we need to add the excess capacity somewhere such that we end up with the 12 units of excess demand, which is hypothetical, and it has a cost of 0 because anything in this cell would be multiplied by this cell, let's say, or anything here would be multiplied by corresponding 0 cost, and the whole thing will not affect our solution, but it helps us match every supply with every demand someplace. Okay. So if we were to produce anything in the regular time or the overtime or subcontracting for the period 1, we would end up utilizing some of the demand that is required. Now it helps us to let's say calculate what I call it unmet demand. Okay, so let's say if I allocated 10 units here, at this point I want to know how much more am I left with, how much more demand do I have to meet, such that I'm not doing the mental calculations here. Okay, so the easiest way to do that is equals to 40, the given number, minus the sum of anything above. Okay, now in this case, because I have this initial inventory, I'm going to add that as well. So let me go a little further, and okay, so then I can copy this. Now in this case, my demand was 40, so I'm only required to produce, let's say if I didn't allocate at this point in time, my demand was 40, but 20 was my starting inventory, so I'm only required to produce 20 in this period. I do not have any initial inventory here. for the month of February, and the demand is 50. Therefore, I need to make all of the 50 yet. But let's say if I make 5 here, 5 here, then I'm only, immediately it updates me as to how much more do I have to deal with the demand that is not met yet. Okay, so similarly, I would call this as unmet, just the way I call this unmet demand. I'm going to call this basically a rough, it's not required, but it helps us calculate balance supply, let's call it, yeah, such that I would say equals to the given supply minus the sum of all the other allocations in that row. So this gives me how much more can I do for that particular period in that category. Okay, so, and I will also color this the same. Okay, so these are my rough cells. It only helps me be accurate when I'm solving the problem. That's all it does. Okay. Now, in the textbook, they say that all these excess allocations are, let's say, reddish in color. So I'm going to color them reddish in color. Okay. Let me do the same then here, so then they don't feel left out. All these reds, too much red, but okay. Anyways, now we are ready to solve. Also, at this point in time, we can also say the total cost of production for this planning period would be simply the sum product that we've been doing since chapter 12, because we know the cost. Yeah, we know the cost including the dummy variable. So make sure you choose the correct set of cells. So as of now, we have 1, 2, 3, and 4. Yeah, so in order to highlight this, let me see if this works. Okay, yes. So we have 1 column, 2 column, 3 column, 4 column, and we are dealing with how many number of rows? 3, 3, 6, and 9, and there are 2 blanks in between. Yeah, so when at this point, when I'll put a comma here, then you have to choose the second array of cells. Make sure they are correspondingly same. So 1 column, 2 column, 3 column, and 4 column, and exactly same. That is why I'm trying to keep this same or correspondingly same, such that it helps us maintain our accuracy in the formulas. Okay, so at this point, this comma 1, 2, 3, 4, and exactly the same. Okay, 1, 2, 3, 4, and the same rows, which we can see. Now, one thing I want to highlight is that there is no such thing when we are dealing, when we are in the February and we have the option to choose regular time, overtime, and subcontracting. There is no such thing as going back into the time in the past and then utilizing it. So to remove confusion, let me put this as well here, like that. Okay, so the first option we have is that in the month of January, or in the first period, you can produce here such that you can also carry it over for the next period, or you can carry it over to the next period, or you can produce regular time in the February itself, which would be here, or you can produce in the regular time of March. That is all the options for the regular time. Now, if you were to produce overtime, you can produce overtime in the month here and then carry it over for the month of February, or carry it further into the March. In here, you can only carry it once, and this is the end of our planning horizon. So that's all we are dealing right now. Now we have to start allocating the numbers such that at any given point in time, let's say I make 10 here, I make 5 here, or I make 5 here. At no given point in time, the sum of everything in the column should not exceed this number, okay? And that is why the moment this becomes 0, we will stop allocating, okay? That is why this number helps. This is what we created, but this is what the rule says, that the sum of everything in the column should not exceed the given demand, and the sum of everything in the row, oops, let me try this color, sum of everything in the row should not exceed the given supply, okay? Because you cannot produce more than the capacity, and there is no point in sending somebody more than what they've demanded, okay? And these numbers in the gray help us allocate these numbers here. Now this is what we are doing manually as of now. Then I'll show you how to do this using linear programming, such that the overall cost of production is minimized, such that the cost of production, if we were to go by 10, 5, and 5, would be 100 times 10 plus 150 times 5 plus 200 times 5. Yeah. So as you can imagine, the more regular time you can use, the more cheaper it would be. Yeah. So that's where this yellow cell, this becomes a target, the total cost of production, such that everything that is demanded is manufactured such that we stay under the constraints, because we have to. I mean, if you don't have the capacity of production, you cannot produce. Now let's see how best we can do. Now in this case, the cheapest option in the month of January is, let's say, if we were to make it regular time, it'll cost us $100. If you make it 150 or subcontracting, it'll cost us even more. So let's allocate to the cheapest cost, which is $100, as much as possible. How much is demanded? Demanded is 40. We already have 20 on hand, so the leftover demand we have is 20. Okay, so let's allocate 20 here. Can we do that? Yes, we can, because if you were to allocate 20, we do have the capacity to produce it, because we have the capacity to produce up to 30, and but we only need 20 because that's the leftover demand here. Okay, so let's do that here. So we put in 20 here. Now immediately you see there's 0 unmet demand, so there's nothing left over. So we are going to theoretically, let's say, cross these. Okay, if we were to do this on pen and paper, such that we do not get confused, we are not dealing with these cells anymore. Also, the balance supply gets also updated immediately. So out of 30 capacity that we had, we already used up 20, so we have 10 more left over, and the cost of production at this point is 100 times 20, which is 2000. Okay, now this is where all the organization helps. Now let's move on to the second period. In the second period, the demand is 50. Yes. So if we were to carry it over, or let's say this is Control D. Okay, for the month of February, our cheapest option is $100. Yeah, which would be here. However, let's say how much is the possible, the maximum possible is 35. Okay, or blue 3 5, because that's our capacity. Now the next option is 150 for the overtime or 200 for the subcontracting. However, if, oops, this should have been here, my bad. Okay, let me do that again. So if we were to do this here, 35, the corresponding $100. Yeah. Now at this point, this cell should update as 15. Okay, and I'll show you in a minute. So that leftover 15 can be produced in overtime in the month of February at the cost of 150 per unit, or maybe we can produce it in the last period and then carry it over here, in which case it will cost us only $104 per unit. So that might be a better option. However, we can only do 10 like that because that's the only leftover capacity from the previous month. We cannot do anything more than that, correct? So at the moment we will put 10 here, this cell would become 5, and then we'll see which is the next lowest cost. Okay, let's catch up to this point. So first thing, 100 is the cheapest one for the month of for the second period. So I'm going to put as much as possible that my supply allows. So I have no more capacity of production left, and I have unmet demand of 15 more. Therefore, of this 15, I'm going to produce in the month of January maximum of 10 I can at the cost of $104. Okay, now my options at this point in time are limited. I cannot produce anything in the previous month because I've used up everything. If I was to produce in last month at the cost of $150 and then bring it over, it is costlier rather than I would use the overtime of my current month. So I am forced to use 5 units for the overtime of the second period. And at this point in time, the demand for the second month is completely met. Okay. Now, similarly, let's move on to the third period. When I move on to the third period, these are my options of the cost. How much is demanded? Demand is 50. How much is available? What is the capacity for me to produce? I can only produce 30 at the cost of 100. So I would assign 30 here. Now, at this point, I can either choose to make at the cost of 150, or I can bring it from the previous period. In the previous period, I have already used up everything in my regular time. So the only thing I can do is, if I was to go previous month, overtime or subcontracting. If that is what I have to do, then I'll have a storage capacity, a storage cost. So it is better to do everything in this period, which is cheaper. So if I was to bring it from the previous period, I would be doing it 104, 154, or 204. 104 is not an option. 154 is costlier. Therefore, I would rather use the cost of 150 overtime of this month. How much is still left? I need 10, and the overtime capacity does allow me to make all the 10s here. At this point, the cost times the number of units I'm making at those costs, my total production cost is $11,790. Now, this is the best we can do by assigning this manually using the transportation method. At this point in time, we do have the leftover demand. How so? Because as you can see from these columns, we'd still have the surplus capacity. So if I was to put 10 here, 5 here, 7 here, 5 here, and 5 here. At this point in time, if I was to, let me bring this over here. Okay. And let me type it in, sum of everything above. Okay. And yeah, so at this point, you can see the total supply is 142, total demand is 162, and the difference between the two is balanced by the initial inventory that we were given for the planning period. However, we have no leftover supply, and we have no unmet demand. This is what is called as making this demand and supply equal while trying to minimize the cost of production. If you were to move away from any of these allocation, theoretically your this cost in production in yellow should go up. Now, if you can find any other cost such that all the conditions of the total supply being equal to total demand being met, and you can find, let's say, any other number that is around this number or any different than this 11,790, that would be called as any other feasible solution. It may not be optimal, which means that may not be the best possible allocation of the quantities at the given corresponding costs. However, that is still one of the feasible solutions. Now, at this point, it completes the what do you call the requirement of the question. But I'm going to show it to you as to how you can also use linear programming to do this. Okay, so let me. I need about this much space more. Okay, and let me copy this. Such that this is the repeat of what we were doing. So let me do this again. 4 equals to this. All of these can be equals to this. So why don't I do this? Okay. Paste formulas only. No, that takes away my blank cells. Okay, sometimes you just can't make the shortcuts. 1 second here. Okay, so the costs are all the same, 104, 150, 200, 104, 150, okay. Now, these are the costs that this time I would ask the linear programming to find for me. These are all the given costs, okay. So these are, I will type them as is. The unmet demand, why did it not copy this? Oh, it is referring to those cells, yeah. Okay, equals to, let's say, how about this? Okay, and this stays the same, equals to some product of everything in here, yeah, comma everything in here. Yes, 4 by 11. Yes, and I can close this. Also, why is this one, what is this referring to? Okay, cool. What is this referring to? Okay, I get it. Equals to the given numbers. Yeah, we calculate these 30, 10 and 5 from here, correct? So these numbers are coming from here, 30, 10 and 5. So instead of scrolling my spreadsheet again and again, I'm just making them equals to the nearest given number. Yeah, so these numbers are given to us. There's no uncertainty about it. Okay, so now let's see how we can set up the linear programming such that we find out the best optimal possible allocations. Okay, so now when we do this using linear programming, I want to calculate the left hand side variable. Okay, in this case that would be sum of everything that I've used so far. Okay, and Okay, and I'm going to color this as let's say blue. Okay, so the blues are the calculated left hand side. Similarly here I'm going to calculate sum of everything on the top. Okay, come on, what now? Okay, yes, including here. So this becomes my calculated left hand side here. Okay, now we can say that all of our left hand side have to equals to the right hand side, and all of our these left hand side have to equals to the given right hand side. And we can say that this is the cells that the solver can change, and this is the function, objective function that it should try to minimize. Yeah, so let me label it for, so then if we have to read the results, then we can read the results. Okay, so let's see, where's my solver? Data, solver. I'm going to reset all and choose, this is my objective function, and I want it to minimized by changing the cells. I'm going to select only the cells that are colored here, comma these 3 by 3, comma these 2 by 2, and then add that all of these blue cells have to equals to these green cells. Okay, now this is only because I have this blank cell, otherwise I could have selected all in one go. Okay, add all these 3 cells have to be equals to the right hand side. All these left hand side variables have to equals to the right hand side variables given here. Yeah, also adding that these blue cells have to be equals to the given. Okay, hit OK. Oops. Okay, what did I do wrong? Okay, all 1 2 3 4 cells have to be equals to the given RHS. Okay, and let's hit solve, and this is the window you will see. And let's say at this point that's what I'm happy with. Keep solver solution. Okay, so this 11,790 is the best possible allocation. Yeah, see. Oh, and I see this is calculated left hand side. Yeah, not the right side. So this is what saves time, and I'll tell you why. Because if you were to do this by pen and paper, then we would be writing the equations such as, to give you an example, okay, if we were to what this spreadsheet is helping us do is this. Let's say 100 x1 plus 104 x2 plus 108 x3, all this going on for all the overtimes and so on, and then at the end we will have that objective function, let's say 100 x1 plus 104 x2 and so on, such that x1 is the manufactured at regular time in period 1, x2 is what is manufactured in period 1 but carried over to period 2, and so on. All of this, the cost has to be, sum of all that has to be minimized. That would have been our objective function, subject to the constraints are anything produced in first period, in regular time, or in overtime, let's say I'm going to call this 1 overtime and 200 x subcontracted in period 1. All of these would be written as 100 x1 plus 150 x10 plus 200 x s1. This has to be less than or equals to the given number 40. So by changing these numbers, we would have this as left hand side variable. This has to be equals to 40, which is represented in this cell, and the total overall, the function here is represented in that yellow cell here. Okay, so it's, as long as you can picturize it and design it in Excel, it helps us tremendously to cut down one, the calculation, second, any possibility of committing an error and being taken for a ride when we think we are doing something right, but actually there's a mistake in there. Okay, so that's about it for this one, and we have, let's say, one more example to go through. The example here is where there's a new manager in Southeastern Airline. Her name is I think Katie Morgan. Yeah. So initially their method was that they have about 120 seats that can go all economy class or all coach seatings, however you want to call it, and they charge them $140. On an average, they book 80 seats there, so they make certain money off of every person, such that their variable cost is 25, which will stay the same, and by doing so they are able to make certain revenue. Okay, so the simplest way to picturize this is we have our formula: fixed cost plus variable cost. Yeah, and if you were to subtract this total cost from the revenue, then you get your profit, right? In this case, we are given what are we given? We are not given anything fixed cost, but we are given revenue. Revenue is $140 per seat, and there's a cost of $25 per seat. So either I subtract it right away and then multiply that by 120 people. That should give me 9,200. Okay, so however you want to do it, it's a very simple calculation. The next time what they're saying is that this 140 is broken down. How is it broken down? It's broken down into, let's say, early booking. Where is it? Early booking, and booking within a week. So $80 and $190. The variable cost is the same. Now by doing so, they book different number of seats. So 65 seats are booked at early price, 35 seats are booked at the last minute booking price. Therefore, the expected revenue would be different in this case. So let's see how that can be done. So in this case, all I'm saying is the expected revenue is $80 minus 25 here, and for the next one I've calculated 190 minus 25. So the expected revenue that is coming, these are not all visible, so home wrap text. Okay, so these are the different revenues that are coming in. Therefore, if you were to multiply the expected revenue per seat times the number of seats booked, then you get two different revenues. If you were to subtract, if you were to sum those up, you'll get the new revenue with a differential pricing. Now, this is coming off of the fact when in the lecture notes you'll see that there's a money left on the table. When if you were to change these pricing in small increments, you can further increase your revenue. However, it is up to an individual's choice if you want to go that far in terms of making the effort of pricing your product differently versus how much gain do you get in the exact revenue. Because in this case, for example, Katie Morgan is able to make $150 more than the last one, when the uniform pricing was existed. Existed in the last manager's term. So it's more about effort versus rewards. However, it's with the Katie Morgan's approach, they can certainly make more revenue by charging different prices for different seating arrangements versus the last one. Now, this is just for example. The reality could be a lot different. For example, for the early booking at $80, instead of booking 65, they could be booking a lot more number of seats, let's say 90 or 100, okay, such that the total capacity of the plane does not exist, obviously, but these numbers are just to show you the example that by charging different prices for different seats, you can increase your revenue for the same relatively number of booked seats, okay. So that's about it. If you guys have any questions, hope you found this chapter interesting, especially this transportation model. This comes very handy. No matter if you're working in produce industry, oil industry, or service industry, this is very helpful. And this is just to re-emphasize the fact that how linear programming is so important. That allows us to find not only the what do you call one of the feasible solution, but also check if that is your best optimal solution. Yeah, this is the problem that I showed you guys. So if you guys have any questions, feel free to contact me. That's about it. Have a nice day. Bye.